Today I'm going to talk about various types of diodes. Earlier we talked about how diodes work. Now I'm going to talk about different types. Let's start with a review of what we talked about in our previous video, which was how modern diodes are constructed from blocks of silicon. Early diodes were constructed from pieces of wire contacting a crystal or from selenium, which were similar, but most modern diodes are constructed from blocks of silicon. Silicon has a property where the outer layer of electrons, the valence shell of electrons, has 4 electrons, and when you put silicon together you get what's called a covalent bond, which has the properties of a crystal that is a non-conductive crystal. But if we infuse impurities into the crystal, we can get particular properties that make the diode. So let's say in this side we infuse some arsenic, which has 5 valence electrons. 4 of those electrons will fit into the crystal structure quite neatly, but the 5th one does not, so it tends to float around. But although those electrons are free to float around, they are attracted to a proton in the arsenic atom, and so the atoms are neutral, but yet the extra electron doesn't quite fit in, so they can float around. Any electron can pretty much move around as long as another electron takes its place, such that they are evenly distributed. And so now that we have those free electrons, we have a conducting material here. We call this N-type material because it's kind of negative, but kind of not. It's actually neutral, but because of these excess electrons, it has a property of negative-ish, if you want to say so. So we call that N-type material. And let's say over here we infuse something like gallium or aluminum, which has only 3 valence electrons. Those electrons fit into the structure, but because there's only 3, it leaves gaps in the structure where an electron could be, and that gap is attractive to electrons, but it's neutral because for every electron in the gallium or aluminum atom, there is a proton to make the atom neutral. So the material is neutral, but there are places where electrons could be, and those places in the crystal structure are attractive to electrons. We call that p-type material. And so that has gaps in there. We'll represent those with little circles. We call those holes. And I explained that they act sort of like the hole on the putting green of a golf course, where when they move that hole around to keep the grass healthy, well, what do? They take a plug of grass and dirt from here and move it into this hole, and so, well, you go out there golfing, it looks to you like the hole moved. Well, it wasn't the hole that moved, it was the grass and dirt, but for all intents and purposes, it looks like the hole moved. So as electrons can move around freely to these holes, or move around freely because they're attracted to them, as the electrons move around, we don't see the electrons move, we see the holes move. And if we try to follow the electrons, it becomes very confusing, so we follow the holes. So we pretend that these holes move, and if we do, it makes it easy to follow what goes on in the material. So we have holes on one side, excess electrons on the other side, p-type material here, n-type material there, and in between we have a p-n junction. And what happens near this junction, well, like I said, these holes are attractive to electrons, so the electrons near the junction will jump into the holes near the junction, so we no longer have free electrons near the junction. And since these holes now have electrons in them, we no longer have holes near the junction, so we have an area called the depletion region. These electrons and holes are called charge carriers. There are no free charge carriers in the depletion region, so we have an area that cannot conduct in there. So we have a conductor, a non-conductor, and a conductor. That will become important in a particular type of diode we'll talk about down the road. Now what happens if we put a positive charge on the N side and a negative charge on the P side, basically a higher voltage here and a lower voltage there? Well, this positive charge is going to pull electrons in this direction. So these electrons, well, I'll just represent them that way. They're pulled in that direction. So there's more electrons toward that positive charge. And the same thing happens over here. Of course, it's really electrons moving, but if we try to follow them, it becomes hopelessly confusing. So the negative charge here tends to pull holes that way. It's really repelling electrons away, but Like I said, in the golf course, it looks like the hole moved, so let's just say the hole moved. So these holes are attracted away from the junction. I'll just kind of draw it that way. Maybe not the best way to do it, but simple to do on the whiteboard here. So if we bias it this way with positive to the inside, negative to the P side, reverse biased, we actually make that depletion region bigger. So does that make the diode conductive overall? No, it just gives us a bigger non-conductive area. And if we put a greater charge there, it just becomes bigger. So it will not conduct unless we put enough charge there to overcome the non-conductive properties, and we get a cascade of conduction, probably destroys the diode. So reverse biased, it doesn't conduct unless we virtually destroy it. Now there's one diode that's a little different. I'm not going to talk about that diode in this video because we have a video just on the Zener diode, but other diodes are normally not used in this way, except for one, which we will talk about in this video, that takes advantage of the fact that we can vary the size of that depletion region with the voltage. But anyway, what happens when we forward bias this? So we're going to move our charges so we have positive on the P side, negative on the N side. What that's going to do is drive these charge carriers toward the PN junction. I'll draw that right back in there. Let's get rid of these lines. We no longer have a, well, the depletion region is now smaller. Let's move everything closer to the junction. And it's still not conducting because we haven't completely closed that depletion region. So if we increase the voltage, that will push these closer together. And now, well, we already have a depletion region because some electrons have jumped into some holes. We had some electrons here and some holes here. The electrons have jumped into the holes, so we have a small depletion region. If we push that depletion region small enough, then more electrons will jump into more holes. And that looks like I just made the depletion region bigger, didn't it? Well, not really, because when we do that, we're going to inject more electrons from the negative charge and inject more holes from the positive charge, and they're just going to take their place. So electrons went into holes and annihilated each other, but more come in to take their place. And so what's going to happen? So it's going to happen again. These electrons jump into these holes, they're gone, more come in to take their place. So what do we have? We have a current. Basically, it's electrons moving in that direction. But once again, if we try to follow what's going on with the electrons over here, it becomes confusing. So we don't worry about what the electrons are doing, but we just say, okay, the electrons are coming in this way, the holes are coming in this way, they meet at the junction, they annihilate each other, and we end up with an electron flow going this way, or back to what we talk about in this class, and that the vast majority of people in the industry talk about, we will say that there is a conventional current flowing in that direction. So when we forward bias it and put enough voltage on there, it's going to start to conduct. This conducting begins to cascade and become a major conducting at about 0.7 volts for silicon and about 0.3 volts for germanium. But as I talked about, that's not etched in stone. Typically, you will find those voltages on a forward bias diode, but as you get more and more current, that voltage will get higher, and some diodes can have much more than 0.7 of a volt, even more than a volt and a half, 3 volts. It seems in my mind that there are some power diodes that can get up to 7 volts when they're forward biased. Maybe I'll put something up here that says a particular one if I'm remembering that correctly, but you can get a lot more than a volt or a volt and a half or even more with power diodes when you get so much current that you get a lot of voltage. But typically around 0.7 of a volt for a silicon diode. Okay, so that's the basics of how a diode works. Now what we're going to talk about are small signal diodes, switching diodes, and rectifier diodes, because those are your basic diodes that we look at this particular principle at how they operate, normal operation where we work them forward biased to conduct, reverse biased to non-conduct. So let's talk about those small signal diodes, switching diodes, and rectifier diodes. The symbol is the typical diode symbol, and they're used for small currents and just as basically electric check valves to allow current to flow one way but not the other way. If they are optimized to switch quickly, meaning that when they're reverse biased, with the positive to the cathode and the negative to the anode, they are like a open switch. So there's basically what it looks like when it's biased that way. But if we reverse that, positive to the anode, negative to the cathode, that's like a closed switch, so it acts like a switch. If it's optimized to do this quickly and efficiently, we call them switching diodes. So it might be a small signal diode or a switching diode. Of course, we have power diodes that can handle a high amount of current. Consequently, they get deeper into that curve where we get more voltage across them. I've seen them rated around 1.5 volts. They might get up to 3 volts maybe, but typically our small signal diodes stay around 0.7 of a volt if they're a silicon diode. So that's your typical small signal or power diode, pretty much just an extension of what I've already said. It's just a diode. However, as you recall, one of the aspects of a diode is that we have our junction, N-type material, P-type material, and we have holes over here, a conducting area. Electrons over here, showing them as little negatives this time, another conducting area with a non-conducting area in between. So is there another component that consists of two conductors separated by an insulator? Well, of course, that is the capacitor. So a diode looks like a capacitor. What happens if we reverse bias it? Remember, if we put positive to the N side and negative to the P side, that makes the depletion region grow larger. So that's like making the capacitor have more distance between the conducting plates, which will decrease the capacitance. So can we use a reverse bias diode as a voltage controlled variable capacitor? Yes, we can. We have diodes optimized for that called varactor diodes. Let me draw the symbol for it up here. It's a regular diode symbol, except the cathode looks like a capacitor, and that is called a varactor diode. Also known as a varicap. So we reverse bias it and control the capacitance with the voltage. These are used in phase-locked loops, which we'll talk about way down the road in analog circuits. And they're used in little FM radios, inexpensive FM radios that you tune by pressing a button and it scans across and stops when it finds a station. That's just two places I know where varactor diodes are used. Okay, another thing that happens when a diode is forward biased is it emits electromagnetic radiation in the high frequencies or very short wavelengths of infrared and visible, and maybe even ultraviolet light or close to it. The symbol for such a light-emitting diode is a standard diode symbol with a little lightning arrow, maybe 2, going from it. So that's a light-emitting diode. The color depends on the materials used. The first commercial light-emitting diodes were made of gallium, arsenic, and phosphorus. And that particular set of materials would produce red light. And then other materials would produce green light. For many years, the only colors of LED we could have were red, green, and orange. We actually had 2-color LEDs that were interesting. You can still buy these actually. It's a red and a green LED in one package, arranged in parallel in opposite directions. So these were in a single package, and one was red and the other was green. So if we put the voltage one way, let's see, that's going to forward bias the red diode, so we get red light. But if we biased it that way, that forward biases the green diode, and that gives us green light. Or if we put alternating current across it and change the bias rapidly, we get both red and green light, or it looks yellow. So that was the 2-color LED, sometimes called a 3-color LED, that would give us red, green, and yellow light. There are other multicolor diodes that work a little differently. The package looks something like this. Instead of 2 wires, we get maybe 3 or sometimes 4. And there's a common connection, a common cathode, and then the 3 anodes, we can get red light, green light, or Nowadays we can get blue light because now we have blue LEDs. We did not have blue LEDs until about the mid-1990s, and then they were very expensive and not very bright, but of course now you've seen plenty of very bright blue LEDs. So we can actually produce white light with those, but it doesn't produce a good quality white light because it's made from three very narrow bands of colors. To produce white light these days, we will use a blue LED, which is near ultraviolet. And so there is our near ultraviolet LED that produces a deep blue light, and that goes to a phosphor screen. Phosphor being a material based on phosphorus, not necessarily actually having phosphorus in it, but when it's hit with ultraviolet light, it produces another color. In this case, it's chemically optimized to produce white light. We might produce a warm white with a little bit of yellow in it. It looks kind of like an incandescent bulb, or a white light that, or maybe a bluish light, sometimes called a cool white, which is more like a regular fluorescent bulb. Car headlights that use LEDs tend to use that color, but ones used for lighting homes tend to be the more warm white. And of course that produces the white light. That's why a lot of white LEDs kind of have a little bit of a blue tint to them, because it's actually a blue light going through that phosphor, but that can be optimized to give us whatever color we need. And of course, LED lights are replacing incandescent and fluorescent lights, so it's a very popular combination of materials for LED lighting. Now another thing about LEDs, we might have light emitting diodes, which emit light when they're forward biased, but also when you reverse bias a diode, it changes its conductance when light falls upon it. So a light sensitive diode or a photodiode has a symbol that looks similar to the LED, except that little lightning arrow or two lightning arrows point to the diode, and this means it is light sensitive. And we use those in a reverse bias condition, so with no light going into it, it's going to have a very, very high resistance or low conductance, but as more and more light falls on it, it conducts more and more, and so we can use diodes to sense light. We also have light-sensitive transistors. I'll talk about them in another video, but light-sensitive diodes or photodiodes react much more quickly to the light changes than a phototransistor does. So that's a good use for photodiodes, to be able to sense changes in light quickly, such as receiving information over a light beam like in fiber optics. And now that we have discussed light-emitting diodes and photodiodes, we can discuss a device you can buy that uses both. It's called an optoisolator. Or an optocoupler, depending on who's talking about it. So it isolates electrically, but couples optically. So it might be called either of these, optoisolator or optocoupler. And so what we have is one package where one side we have a light-emitting diode, and the other side of the package we have a photodiode. Sometimes it might be a phototransistor, either one will do, but like I said, photodiodes react more quickly than phototransistors. And so the light going across from the diode to the other diode will transfer information. So if we turn this on and off, we get basically a switch that turns on and off, or anywhere in between. And so we can use this to pass information from one circuit to another with no electrical connection. So that would be an optoisolator or an optocoupler. The next common type of diode to talk about is the silicon-controlled or silicon control rectifier, depending on who's talking. Also sometimes called a thyristor, named after the thyratron tube, which is a vacuum tube that acts similarly. The SCR, or silicon control rectifier, is a 4-layer device. So instead of one p-n junction, we have 3. So it's something like p-n, p-n, and we have a connection here and a connection here, and one of these, I don't remember off the top of my head which, I'll just put it to that one, has a third connection called the gate. So we have the anode and the cathode and the gate. The symbol for this device is a regular diode with a extra, I'm going to draw it this way, little extra connection called the gate. So anode, cathode, and gate. And if we reverse bias a silicon controlled rectifier, or SCR, it just acts like any other reverse bias diode. If we forward bias it, nothing happens until we trigger it by putting a voltage on the gate. So gate is a good term because it's like a locked gate. Nothing can come through the gate until you unlock it with the trigger. But once it's triggered, it will remain open or conducting until we remove the power from it. So it doesn't conduct until we trigger it, then it continues to conduct until we completely remove the power from it or reverse bias it or whatever. So think of it like a pin holding in a herd of elephants. And there's a gate on the pin. You open that gate, here come the elephants. Are you going to be able to close that gate? Not until all the elephants are through. So that's the way a SCR works. The gate triggers it to conduct, but will not stop conducting until you completely remove the voltage from it or reverse bias it. Another similar device is called a triac. It's also a 4-layer device, except it has 2 gates. So there's our 4 layers. Anode, cathode, 1 gate, another gate. Now I'm really oversimplifying this, but just showing you that they are 4-layer devices just for your edification. And the triac is like 2 silicon controlled rectifiers in parallel in opposite directions. In a single package, of course. So there's 1 gate, there's another gate. They are connected together and they come out of the package. And so we have 2 connections. I'm just remembering, are they called both cathodes or called both anodes? I think they're called both anodes. Correct me if I'm wrong, I'll put a correction up there if I'm wrong. So anode 1, anode 2, and then the gate. And of course this then works either direction. The other SCR only works in one direction, this works in either direction. So if we bias it this way, nothing happens until we put a trigger on the gate. If we bias it this way, nothing happens until we put a trigger on the gate, and it works either way. These are used in light dimmers where, if we look at the alternating current going to a light bulb, this goes through a circuit such that, here's our 0 volts, such that we bias the triac, but nothing happens until we trigger it at some point, and then it conducts for the rest of that cycle. But when it hits 0 volts, it stops conducting. And so it doesn't conduct until we trigger it again, and then it conducts until it hits 0 again. And we can control this trigger point by a capacitive delay or other circuit so that we can trigger it anywhere along this. So if we trigger it like here, it only conducts for a very short time. Or if we trigger it here, it conducts for a long time. So we get brighter light or dimmer light. And those are used for light dimmers or variable speed motor controls. So there's the triac, the basic idea of a motor control. We can talk about those in a different time. We just want to talk about the basic component right now. When we're talking about SCRs and triacs, we'll talk about the Shockley diode. So here is the symbol for the Shockley diode. If I can remember how to draw this, I think it's like that. Shockley diodes are named after William Shockley, who is credited with inventing the transistor, although it was really his team of Brattain and Bardeen who developed it. He just got the credit for it. But anyway, that's named after William Shockley. They don't make them anymore, but there is a high power equivalent made called a Thyristors. Now when we're talking about the Shockley diode, let's talk about the Schottky diode. So that's a Shockley diode. There's another one called, which is not to be confused with it. We'll draw the symbol for the Schottky diode. And its claim to fame is very low forward bias voltage. So if you have a circuit where you want to have a diode but have lower than 0.3 volts for the turn-on voltage, you would use a Schottky diode. And there is the symbol for it. They do have a lower turn-on voltage, but they do have more reverse leakage voltage. So we get an advantage, but then a disadvantage. Now I should have talked about the diac, but I guess that's appropriate here too, because it's closer to the SCR or the triac, but it sort of acts like a Shockley diode that works both ways, so it could be appropriate here. Here is the symbol for the diac. I forgot to give the symbol for the triac. Well, there's the symbol for the triac. So we have two anodes and one gate. We remove the gate, we have a diac. So it's like a triac with no gate, so it turns on at a certain voltage. These are often used to trigger SCRs or triacs. And finally, the tunnel diode. To talk about the tunnel diode, I need to look at the entire voltage versus current curve. So I'm going to draw the graph up here. And this is going to be the forward biased region over here and the reverse biased region over there. And as we said before, a normal diode, as I forward bias it, I'm going to get almost no current, and then when I get to the turn-on voltage, about 0.3 volts for a germanium diode and about 0.7 volts for a silicon diode, it's going to turn on. I'm going to go ahead and draw that just because it will be useful. So there's your standard diode curve. I'll put that at about 0.7 volts. And then reverse bias, the normal diode is going to have almost no current, and then it's going to reach the breakdown voltage and suddenly a lot of current, and that's probably going to destroy the diode. The tunnel diode, when it's reverse biased, it looks pretty much like a resistor. So there is the reverse bias curve. As I increase my voltage, I increase my current, and of course this is going down because I'm just showing that when it's reverse biased, I have negative current. What does negative current mean? It just means the current's going the opposite direction. So if we have a tunnel diode, there's the symbol. If it's reverse biased, I'm going to get conventional current flowing that way. If it's forward biased, I'm going to get conventional current flowing that way. So negative current's just flowing the opposite direction. So here we are reverse biased, and as I increase my voltage, I get more current. And it's proportional, so I get a straight line. Looks like a resistor. Let's go the other way. I'm going to decrease my voltage. So as I decrease my voltage, my current decreases, and eventually I reach where I have 0 volts, and therefore I have 0 current. Still looks like a resistor. Now it's going to become forward biased. Positive to the anode, negative to the cathode. And as it crosses the 0 point here, I'm going to get a line that looks like a resistor again, about the same slope. So it still looks like a resistor. So what's the point? Well, I get to a certain amount of current, and the current starts to settle down and heal over, and I get to a maximum current, and increasing the voltage decreases the current. I'd like to draw this a little more. It just doesn't look quite right. So let's just redraw this real quickly. So here is our reverse bias region crossing the 0 point. Pretend that's going right across the 0 voltage and 0 amps point there. It reaches a maximum current and then heals over, and then as we increase our voltage, we get less current. So now here I increase my voltage, current goes down. Decrease my voltage, current goes up. What should we call that? Well, if we increase the voltage and the current goes up, that's what a resistor does. But if I increase the voltage and the current goes down, that's the inverse. Why don't we call that negative resistance? So I increase the voltage, current goes down. We have a region here where we have negative resistance. But then we get down to a certain point and it heals over again and starts to go back up, and it intercepts the normal diode curve. So the normal diode curve is going to be something like that. And so above about 0.7 volts, it looks fairly much like a regular silicon diode. But this is the interesting area, the region we're interested in, the negative resistance region, because we can bias this such that the voltage and current starts to oscillate in this negative resistance region, and it can oscillate very, very fast, much faster than any transistor. So if we want an oscillator that works at a very high frequency, perhaps in the gigahertz range, the obvious choice would be a tunnel diode to make that oscillator. So there we have tunnel diode with its negative resistance, and that we can get it to oscillate there and be the source of very, very high frequency oscillations. So those are the main types of diodes we need to know about. I'll have another video dedicated to just the Zener diode later. I hope you found this video useful and informative. If you did, please give me a thumbs up down below. It really helps the channel. And I could not make these videos without my patrons at Patreon. To help me put these videos online and help keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy. A big thank you to my patrons, and thanks to everyone for watching.